We're going to keep working on this same ALEKS problem, calculating the reaction rate of one reactant from that of another. So we've already done one of these problems, and you know that the very first thing that we're going to have to do is write a balanced equation for the reaction that's taking place, because we need those stoichiometric coefficients. So we're going to read the problem to get the balanced equation. Dinitrogen gas, N2, combines with dihydrogen gas, H2, to produce ammonia, NH3. And we need to balance this equation. I'm looking at 2 hydrogen on the left versus 3 on the right, so I need my stoichiometric coefficients to be 3 and 2 for those two guys, and then it looks like the nitrogen has balanced itself, so that's perfect. So now that we have our equation balanced, let's figure out what we're working with. We're being given information 992 liters per second of dinitrogen, so that's the rate of the N2. And it wants to know the rate at which ammonia is being produced. So we're looking at 3 different types of rate here. We have the rate of the N2 all by itself, not a reaction rate. We have the rate of the ammonia, NH3, that we're trying to figure out. And then we also have the overall reaction rate. And these are going to be usually, well, I shouldn't say usually, these may be the same numbers, they might be different numbers. So the rate of the N2 is just simply the change in the concentration of N2 over the change in time. And because N2 is a reactant, it's a negative number. The rate of the NH3 is the change in concentration of the NH3 over change in time, and it's a positive number because it's a product. For the reaction rate, this is where we are factoring in the stoichiometric coefficients. So for the reaction rate, we could say negative change in concentration of N2 over delta T, the stoichiometric coefficient is 1, or we can say delta NH3, the change in concentration of NH3, over 2 delta T. So for the reaction rate, that's where we include stoichiometric coefficients so that we get the same value of rate no matter how we're calculating it. So here's the 3 things that we're working with. And the problem tells us that the rate of the dinitrogen, so that's this guy over here, 998 liters per second. And that is 998 liters per second is negative delta N2 over delta T, negative delta N2 over delta T. So we know that that's 998 liters per second. Now, if you're wondering why is the negative sign going away, the term negative delta N2 over delta T, the whole entire term is 998. So it's built into there. And our goal is to calculate the rate at which ammonia is being produced. So this is what we're trying to figure out. This is what we're trying to figure out right here. So this is our goal, delta NH3 over 2 delta T. If we multiply both sides of the equation by 2 times 998 liters per second, then we're going to get the change in concentration, the rate of NH3 per time. So let's get that. 2 times 998 is 1996 liters per second. And that's right up here. Now, just like the first one that we did, we have a unit issue. So kilograms versus liters, and that means that we're going to have to do a liter to kilogram conversion. And like the last problem, we're going to do this using the ideal gas law. So we are going to use PV equals nRT. I've just rearranged it right there. We're going to solve for N, the moles, and then convert that to grams and convert that to kilograms. Our pressure is 0.42, and again, I'm leaving units off to save space. Our volume in liters is 1996. R, the ideal gas constant, is 0.08206. Temperature in Kelvin, 299 plus 273. Our temperature is 572. And so this is going to give us 0.42 times 1996 divided by 0.08206 divided by 572. That gives us 17.9 moles of, let's not forget what we're working with, 17.9 moles of NH3. I'm going to bring my work down to the bottom here. 17.9 moles of NH3. We want to convert that into grams of NH3. 14 plus 3 is 17 grams per mole. And then convert from grams into kilograms. And we are going to get, let's make some space up here. Our answer is 0.0, nope, that's not it, 0.30 kilograms per second.